Here are a couple examples where you might want to use a chi-squared test of independence. So if you want to know if color preferences are different for car drivers and truck drivers, or whether preferring cats or dogs depends on what state you were born in, notice here that in both cases, what we have going on is we have two categorical variables. In the first case, we have the color of the vehicle. That's one of our categorical variables. And the other one is if they drive a car or a truck. Now, in the second question, we have preferences, cats or dogs. That's one categorical variable. And the other one being the state you were born in. Okay, so we need two categorical variables. And we want to know if one of those values in some way depends on the other. Now, we're talking about independence here in terms of probability. So, does whether or not you have a blue vehicle change the probability of you driving a car or a truck? That's the kind of situation we're talking about. In a chi-squared test of independence, the null hypothesis is going to be that our two variables are independent. The alternative is going to be that the variables are dependent. If you reject the null hypothesis, you're saying we have proven that the variables are not independent and therefore they must be dependent. If you fail to reject the null hypothesis, that means you haven't ruled out the possibility that they're independent, which is not the same as proving that they are independent. We're going to compare what we observed, so our observed frequency from the sample, to what we expect to see based on the assumption of independence. So this is very much in the same vein as a chi-squared goodness of fit test. The test statistic is essentially the same as it was for the goodness of fit test. We're going to compare what we observe to what we expect and measure how far off those two things are from each other. Now, the big difference here is in the degrees of freedom, and we'll explain where those degrees of freedom come from in a minute. Okay, but they are the number of rows minus 1 times the number of columns minus 1. And the number of rows and columns depend on how many options there are for each of your two variables. So we're measuring two different things about each of our observations. So we have two variables to worry about. So the rows are going to represent the different options for one variable. Okay, so that might be the color of the vehicle, for example. And then columns will represent the possible values or categories of the other variable, car, truck. So we collect the data and we look at each observation and see which combination of traits that particular observation has. And so we end up with a table full of totals or observed frequencies saying, here's what's happened. Okay, we had 83 people who are driving green trucks. We had 54 people driving red cars, and so on. In calculating our expected frequencies, we need to know the row and column totals for each of the different options within the two variables. So we'll add all those up first. Now, to calculate the expected frequencies, we need to take these row and column totals, and not the breakdown within the subcategories, but just how many total blue vehicles, how many total red, how many total trucks, how many total cars. Okay, so we need those row and column totals. And from there, we're going to create our expected table. And so we're going to just transfer those values to our new table. And then we're going to calculate the individual combinations of the cells and what we expect those frequencies to be. Calculating the expected frequencies for each row and column combination depends on the probability of an observation being in that row and column subset and how big our sample size is. So we need to figure out the probability of an observation being in a particular row, row I, and a particular column, column J. So that is the probability of having a certain combination of traits of our two variables. This is simply going to be the probability of observing whatever the row I variable is, times the probability that an outcome would be in column J, assuming our variables are independent. And that is the null hypothesis of our test of independence. Now, to find the probability of getting an outcome that's in a particular row, well, we would take our row total, because that's how many we had in that row, divided by our sample size. And then to find the probability of being in a particular column, it would be the column total over the sample size. So assuming independence, the probability of getting an outcome that's in a particular subcell of our table is equal to the row total divided by n times the column total over n. So just like with the goodness of fit, like we said, how many we expect to be in each subdivided category is based on the sample size and the probability of being in that category. Okay? And we just determined, right, that the probability of being in a particular row and column combination is the row total over n times the column total over n. So when we multiply that by n, we're going to get two of these n's to cancel out. And we're going to be left with this shortcut formula that says how many we expect to be in a particular cell within our table is going to equal the row total times the column total divided by the sample size. So let's look at this a little more closely. We talked about degrees of freedom a little while ago. So I want to divide up my observations into two groups. So I want to ignore this last row and the last column here on the right. Okay, and I want to focus in on all the columns before the last one and the rows before the last one. Okay, so once we have calculated those expected frequencies, right, so once I've gotten all the columns in row 1 except for the last one, remember we already know the row total, therefore that last value in the column has to be whatever's missing. Okay, so if we look at this, the number of cells that are in the first rows minus 1, and the number of columns is the columns minus 1. So when we multiply together those two quantities, we get how many cells there are that are free to be whatever they want. So that's our degrees of freedom. Those are all random numbers. Okay? But once those have been set, right, the values in the last row and the last column are not free. Right? They have to be the number that is missing to make the row and column totals add up to what they're supposed to be. Okay, so that's where we get our degrees of freedom calculation from. We have our observed frequencies from our sample. We know how to calculate the expected frequencies. That's going to be based on our row and column totals and the sample size. And our assumption that the null hypothesis is correct. That is our assumption that the variables are independent. We have our familiar test statistic. Just like the goodness of fit test, we have a minimum of 5 expected values needed in every category. Okay? And as long as that's happening, then we are good to go ahead and perform our test of independence. So once again, the basic format of this formula is not new to us. It measures how far off what we observe is from what we expect. Okay, so it's measuring this grand error in our model, in our assumption of independence. Okay, so the farther apart our observations get from what we expected, assuming independence, the bigger O minus E is going to get, positive or negative, and when we square either one of those, we're going to get big results. So if we have big error terms and we add up big error terms, they're going to add up to a big chi-squared score, which is why the test of independence is always a right-tailed test. So let's look at an example. We're going to consider people riding the T. Okay, and typically T's show up anywhere from 8 to 10 minutes depending on the time of day and route and traffic and everything else that's happening around campus. And we're going to define a short wait as any wait that's less than 4 minutes. So you get in line at the bus stop, bus shows up in under 4 minutes, we're going to call that a short wait. Okay, anything longer is going to be a long wait. And the question we have is, do the wait times depend on the route? And we're going to use 0.05 significance level, which is absolutely the most common for any test of independence. Our null hypothesis is that the variables are independent, so the wait times and the routes are independent. Our alternative is that they are dependent, so the wait times do depend on the route. Here's the data that I've collected. And so we're going to use this. This is our observed values. We have 81 people who had short waits for the hill route, 54 people with long waits for the hill bus, and so on. So from here, we're going to calculate our expected frequencies. To calculate our expected values, we start by copying our table and duplicating just the row and column totals. And then we're going to calculate the expected frequencies of the cells using our row total times column total over n formula. So for our first case, right, we have short waits. Total of the short wait row was 221. Hill column total is 135. So I've got 221 times 135 divided by the sample size of 377. And we're going to do the exact same thing for each subcell. So for the fort, 221, that's our row total, right, for short waits. And the column total for the fort was 137. Move on to the Nealon route and short waits. Again, still row total 221, column total is 105. And now we're going to move down to the row with the long waits. So our row total is going to change. And then we just finish off each calculation, going cell by cell, row after row, column after column. And now we need to simplify those numbers. So I've done that. And here we have our simplified expected frequencies. And I've rounded to 2 decimals just to save space. It would be more accurate to keep more decimal places on our expected frequencies. And it's perfectly fine that they didn't come out to be whole numbers. Now, looking at our expecteds in blue here, right, our smallest one was 43.45, so that we definitely have all of our expecteds over 5, so we're good to go with our hypothesis test. So we're going to start with our first category, right, short waits for the hill route. We observed 81, we expected 79.14, so O minus E, observed minus expected. Square that, divided by 79.14. And then move on to another category. Now, because we have more columns than rows, I'm just going to go across each row and then move on to the next row at the end. So for the fort route, when it comes to short waits, we observed 72. We expected 80.31. We're going to add to that the amount of error we have for the Nealon route with short waits. And then we'll move on to the long waits. And just take it one at a time. Observed minus expected squared over expected. Do it again for the next category until we run out of categories. Now, in this case, we had 2 options for our row variable, short waits and long waits. And we had 3 options for our routes, the hill, fort, and the Nealon route. So that is 2 times 3, 6 subcategories. So in our test statistic, there are going to be 6 terms added together. So let's talk about the degrees of freedom here. Right? So we had 2 rows minus 1 and 3 columns minus 1. That's going to give me 1 times 2. That's where the 2 degrees of freedom is coming in. And my test statistic, if you multiply all this out, add all these pieces together, is approximately 3.8170. Remember, this measures our total error. So assuming independence, this is some quantitative measure of how far off our results are from exactly what you'd expect if our variables were in fact independent. Now that we've got our test statistic calculated, it's time to find our p-value. Okay, it's a right-tailed test. So our p-value is going to be the area to the right of our test statistic, 3.817. Okay, we have 2 degrees of freedom. We're going to use our chi-squared CDF to find this area. So we want to go from 3.817 to infinity with 2 degrees of freedom. We have a p-value of approximately 0.1483. Compare that to alpha. That p-value is not less than alpha. So we have failed to reject the null, which means we can't support or have not proven the alternative to be true. Okay, so now that we've done all the math, let's remind ourselves, right? The null hypothesis was that the wait times and the routes are independent. The alternative is that the wait times do depend on the route. Okay, and we failed to reject the null hypothesis here. So we cannot rule out beyond a reasonable doubt, beyond our significance level 0.05, right? We can't rule out that the wait times and the routes are independent. They might be. Okay. Now, because of that, that means we don't have enough evidence to prove the alternative, which is that the wait times depend on the route. Let's move on to another example. So here we're going to look at where students live. Okay, so living on campus or off campus but at home, or living off campus on their own, and the year in school they are. So we're going to see if those two things are independent or dependent. So the null hypothesis will be that where students live is independent of their year, and the alternative is that where students live depends on their year. Here's my data table from what we've observed. So we have a sample of 1,898 students and a breakdown of their living status based on what year in school they were. So I've copied over the row totals and the column totals. And then we're going to calculate each of our expected values by doing our row total times the column total over n. Again, so I've got all the row totals in red, all the column totals in blue, so it's easy to see all the numbers. We got 12 subcategories because we had 3 living states and 4 classes. So 3 times 4 is 12. And then we just need to simplify all 12 of those. And now that we have our expected values calculated, it's time to calculate our test statistic. And we have so many here, and to save some space, I went ahead and rounded to 1 decimal place. Looking at our expected frequencies, right, the smallest one I see is seniors living at home, 55.2. So given that, we definitely have more than 5 in each of the 12 subcategories. So for our test statistic, for each combination, we're going to have to compare what we observed to what we expected, right? And so here's what we get. Simplifies down to a grand total of 297.65 for our test statistic. And that's a chi-squared score with 6 degrees of freedom. And we get that by doing our row total minus 1. So again, we have 3 living states on campus, at home, and off campus. So we have 4 classifications, freshman, sophomore, junior, senior. So 3 minus 1 times 4 minus 1, that's 2 times 3, 6 degrees of freedom. And again, to get our terms within our test statistic that added up to that 297.65, right? I just started with the freshmen who are living on campus and systematically worked my way through the table, calculating each one of the air terms, right? So went through the on-campus, then at home, then off-campus. Observed minus expected squared over expected in each case. Now that we have our test statistic, it's time to calculate our p-value. So we need the probability of getting 297.65 or higher for our chi-squared score. Now remember, the chi-squared with 6 degrees of freedom has a mean of 6, so 297 is way the heck over to the right side of the world. So it's not a surprise that our p-value here turns out to be tiny. Remember, 2.6 times e to the negative 61st is 2.6 times 10 to the negative 61st power, or in other words, 0.0060 zeros later to 6. Now there's a tiny p-value, way less than the alpha we currently have, less than any other alpha we've ever thought about using. So we are rejecting the null hypothesis and supporting the alternative, and we are as convinced about this as anything we can ever be convinced about, statistically speaking. Again, so as a reminder, right, of our null and alternative hypothesis, and so we are rejecting the null and supporting the alternative. So based on this data, we are concluding emphatically that where students live does in fact depend on their year in school. So that's chi-squared tests of independence. Good luck. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!